Welcome back to the next session, students. Here we are going to see the signal conversion process, analog to digital, digital to analog conversion process that we will discuss here. So, analog to digital, digital to analog conversion. So, analog to digital conversion to properly acquire an analog voltage signal for digital processing. The following components must be properly selected and applied in this sequence. So buffer amplifier, low pass filter, sample and hold amplifier, analog to digital converter and computer. So these are the components are required. The buffer amplifier isolates the output from the input. So it draws negligible current from the power from the input. And provides a signal in a range close to but not exceeding the full input voltage range of the AD converter, that is analog to digital converter. So analog to digital conversion, here a low pass filter is necessary to remove any undesirable high frequency components in the signal that could produce aliasing. So aliasing is a process where overlapping of different frequency signals, so that should be eliminated. The cutoff frequency of the low pass filter should be no greater than half the sampling rate. The sample and hold amplifier maintains a fixed input value from an instantaneous sample during the short conversion of time of A to D converter. The converter should have a resolution and analog quantization size appropriate to the system and signal. The computer must be properly interfaced to the A to D converter system to store and process the data. The computer must also have sufficient memory and permanent storage media to hold all the data. So here, this is the model A to D converter. There are types of A to D converters, and here you have sensor, you have buffer amplifier, and low pass filter, and sample and hold. Here the quantization process takes place, and this becomes the signal. This is analog signal that actually becoming the discrete signal through A to D converter, and that is sent to computer memory. So this is how the signal is manipulated to become the digital signal, digitized signal, and that will be stored or that may be processed further in the computer. So DAC, digital to analog converter, it is the vice versa process to earlier process. In an electronic circuit, a combination of high voltage plus 5 and a low voltage 0 volt is usually used to represent a binary number. For example, a binary number 1010 is represented here uh, by DACs or electronic circuits that convert digital, usually binary signals, for example 1000 100 to analog electrical quantities, usually voltage, directed related to the digitally encoded input number. Here, this is the state. 5 volts is one binary digit, and the weighing factor is 2 to the power of 3, and 0 volt is 0 in binary, and that is 2 to the power of 2. 1 is zero point 0.5, that is plus 5 volts, so that is 2 to the power of 1, 2 to the power of 0. So 0, 1, 2, 3. So powers are getting increased here for the input signal, that is digital and analog signal. So DACs are used in many other applications such as voice synthesizers, automatic test system, and process control actuator. In addition, they allow computers to communicate with the real analog world. So here input is binary number and it is through register, and the register is a temporary storage element. And here voltage switches. So here depending on zeros and ones, these switches act. And resistive summing network, so this is a type of DAC, it is a type of DAC. And you have amplifier, analog to voltage input is the output from the amplifier. So analog voltage output is obtained from this amplifier as output. So register used to store the digital input, let it remain a constant value during the conversion period. Voltage similar to an on-off switch, it is closed when the input is 1, it is opened when the input is 0. Resistive summing network, summation of the voltages according to different weighting. Amplifier, amplification of the analog according to a predetermined output voltage range. So it is operational amplifier only. So the most popular type of resistive summing networks are weighted binary resistance type and ladder resistance R2R type. These are the two main types of DACs. So ADCs, there are different types. Among them, these are most popularly used types. There are many methods are used for converting analog signal to digital form. So five most commonly used methods are listed here. One is staircase ramp, successive approximation. So successive approximation is very popular technique. Dual slope voltage to frequency, parallel or flash type. So these are the types of ADCs. And a small comparison I am showing here. So type of ADC speed is good, so success of approximation is good, but price is more, and noise immunity is not that much, and the conversion time is constant. So it is always showing the constant. And the other types, if you see among this, parallel or flash is also good speed, but price is very high, and noise immunity is also not that much good. So in terms of noise immunity, we have voltage to frequency, dual slope. And dual slope, according to the conversion process, it vary, the conversion time is not consistent here. And whereas here voltage to frequency, it is a constant type. So when you compare, this is the best method, successive approximation method. So in practice, an ADC is usually in form of an integrated circuit IC. ADC 0808 and ADC 0809 are two typical examples available of 8-bit ADC with 8 channel multiplexer using successive approximation method for its conversion. So here ADC 0808, so this is the chip. It is also integrated chip, and it is National Semiconductor. It is produced by National Instruments. So this is the block diagram of ADC. This is 8 analog inputs. So 8 channels multiplexing switches. It is architecture. It is actually architecture, and you have address latch and decoder, and 3-bit addresses are given here. So address latch enable is pin is one of the pins here, and power supply VCC and ground, and this is the comparator, and this compares both the 8-channel multiplexing output and also switch tree output. So here you have successive approximation register, and you have control and timing circuit, and this is 8-bit ADC. It is a 8-bit ADC only, and the output is from output latch buffer. So the output is taken here, and this is the end of conversion signal to control and timing unit. And once the conversion process over, end of conversion signal will be enabled. So here this is 256R resistor ladder, and here this is the output enable signal to the output latch buffer. So this is another ADC, and this is of 0809 type that we have seen in earlier slide. When the ADC is connected to a computer, the sequence of operation is listed here. The computer reads the end of conversion to check the ADC is busy or not. If the ADC is not busy, then the computer selects the input channel and send out the start signal. Otherwise, step 1 is repeated. The computer monitors EOC, that is end of conversion. When the EOC is activated, the computer reads the digital output. When there is more than one ADC being linked to the computer, they can be connected in parallel also, where using the output enable can do the selection of ADC output. So this is how the ADCs are connected. Selection of DAC. For selection of AC DAC, there are several parameters that can determine the suitability of the particular device. So that is one is resolution, the number of bits making up the input data word that will ultimately determine the output step voltage as percentage of full scale output voltage. So here to calculate the resolution of 8-bit DAC, resolution is 8 bits, percentage is equal to 1 by 2 to the power of 8 into 100 percentage, that is 0.391 percentage. So another parameter is output voltage range. This is the difference between the maximum and minimum output voltages expressed in volts. Example, calculate the output voltage range of a 4-bit DAC if the output voltage is plus 4.5 volts for an input of 0 and plus 7.5 for an input of high, that is 1111. So solution here, 7.5 minus 4.5, 7.5 minus 4.5, so that is 3 volts. 3 volts is the output voltage range. Next is accuracy. This is also important factor. The accuracy is usually expressed by the error in output voltage compared with the expected output voltage. The higher the accuracy, the lower will be the error. Due to the incremental nature of the digital input word, an error can be tolerated, but it should not exceed plus or minus half low LSP or half resolution. So here the example, the error of full scale for an 8-bit DAC with 10 volts, maximum output is 50 millivolts. Calculate the error and compare it with the resolution. So here error equal to 0.05 divided by 10 into 100, that is 0.5 percentage. Resolution is 1 by 256 into 100, so that is 0.391 percentage. So half resolution is 0.195. So this is how the accuracy can be related with the error and resolution. The accuracy is not a good as the error is half resolution, but for many applications it is quite satisfactory. Some commercially available DACs have their accuracy specified as worse than half resolution. Sources of errors may be broadly classified under 4 categories: non-monotonicity, non-linearity, scale factor error, so offset error. And then we have settling time, the time taken for the applied digital input to be converted to an analog output. Typical period can be as low as 100 nanoseconds, making DA conversion a very fast process compared with those of AD conversion. So next is input coding. The digital input can be binary format or it can be in binary coded decimal format depending on the application. Binary format is more commonly used format. So binary coded decimal, that is represented in four numbers. A method of using binary digits to represent the decimal digit 0 through 9. A decimal digit is represented by four binary digits as shown below. So 0 is represented 0, 1 is represented 0001, and 2 is represented instead of 100010. So 3, similarly up to 9, it is represented in terms of 4 digits. So that is BCD number. It should be noted in the table that the BCD coding is binary equivalent of the decimal digit. So each decimal digit is represented. However, BCD and binary are not the same. So for example, 49, that is decimal number, in binary is 110001. So that is binary. Whereas in BCD 0100011001. So this is BCD. So 4 is represented with the four digits, and 9 is represented in 4 digits. So that is each decimal place is represented with the 4 digits. So that is the that is BCD numbers. Each decimal digit is converted to its binary equivalent. So selection of ADC, the parameters used in selecting an ADC are very similar to those considered for a DAC selection. So error accuracy, quantizing error represents the difference between an actual analog value and its digital representation. Ideally, the quantizing error should not be greater than plus or minus half LSB. Resolution is 0 volt to cause 1 bit change in output. Output voltage is input voltage range. Output settling time, conversion time. Output coding, it is usually in binary. So these are the selection factors. And to measure an AC voltage at a particular instant in time, it is necessary to sample the waveform with a sample and hold circuit. So this is known as sample and hold circuit. Input is given through this amplifier, and this is hold. Hold can select either terminals, plus or minus terminal, and this is sample input is given to this circuit. So this is op-amp, and output is output to ADC. So here this is sample and hold circuit. More about sample and hold circuit we are going to see in next session. So we stop here, and for this also you can refer Rai Chaudhary book LIC, Linear Integrated Circuits by Rai Chaudhary. We stop here, students. Thank you. Thank you, students. We'll meet in next session.